Okay, so writing the Lewis structures for a molecule with resonance. So what resonance means basically is that in your structure, you usually will have to draw like a double bond or a triple bond, and there's more than one equivalent place to put it in terms of like wherever you have put that double bond, the formal charges of each atom in that structure would still be the same, right? It doesn't change if you put it in a different position, right? So if the formal charges are equivalent between both of those two possible structures, and that would be what we would call a resonance structure. So what that actually means in terms of like imagining it, if you like, is that remember we don't really sort of pin electrons down in terms of their position and momentum, right? Quantum tells us this. So like when you have an option of having like a double bond between two atoms and a single bond between another two atoms in the molecule, on average, what you actually see is a hybrid between them. So remember, the electrons are constantly moving. So we call this like a resonance hybrid. It's like an average of all the possible resonance structures that there are in our Lewis model for that particular molecule or polyatomic ion. So just remember that the electrons are constantly moving around and switching between these different possible resonance structures at all time. Okay, we can't just like take a snapshot and be like, hey, that's what the structure is, because electrons don't do that. Okay, so let's work through this one. So we're asked to count the valence electrons first. So our valence electrons for selenium dioxide. So we've got 1 times selenium, so that's 1 times 6 valence electrons. We got 2 oxygens, so that is also 2 times 6 valence electrons. So we got a total of 18 valence electrons in our Lewis structure. Ooh, this hasn't come up before. So both selenium and oxygen have got 6 valence electrons, so they've both got a bonding capacity of 2. So which one are we going to make the central atom? Well, another rule, so this is your tiebreaker, right? So if bonding capacity doesn't help you, so the central will be usually the one with the lowest electronegativity. Okay, so that helps us pick selenium out the tiebreaker because oxygen is going to have a higher electronegativity than selenium. Remember, electronegativity increases across a period until you get to fluorine, noble gases. Don't care about, right? And it increases going up a group. So fluorine is always going to be the most electronegative element, and like francium would be like the least. Okay, so now we can sketch out our molecule that we're going to have selenium in the middle. We're going to join them up with single bonds because that is how we roll. And then we're going to give our peripheral atoms some nice juicy lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we've only got 16 valence electrons. So our structure's not quite there. We need to add more. Okay, so we've got to get to 18 valence electrons. So this is where we can add lone pairs to our central. So 1 will do. So now we're good. Now we have got 18 valence electrons. Okay, is selenium happy? Does it have an octet? No, it's got 2, 4, 6 electrons, so sad selenium. So there is a way that we can fix that, which is by taking a bonding pair, sorry, a lone pair, and turning it into a bonding pair, so creating a double bond. But as you can see, we could pick either oxygen to do that. Okay, they would be equivalent in terms of like the formal charges. We'd still have one oxygen with the same formal charges and one with the same formal charges based on the number of lone pairs versus bonding pairs, etc. So let's do it both ways, right? So I'm going to first of all convert this lone pair to a bonding pair. Hopefully I can gently erase it. No, didn't work. One more time, come on. Yes, okay. So that is option A. Okay, and then option B would be, no pun intended, this. Okay, so then we have our double bond on the other side of the molecule and fill in our lone pairs of electrons accordingly. So these are 2 equivalent Lewis structures, right? So both oxygens would, one, if you want to work out the formal charges just for fun, right? So the formal charges of the oxygen with 2 double bonds and 2 lone pairs would be 6 for the formal charge, minus half of the bonding pairs would be -2, minus your lone pairs of electrons would be a formal charge of 0, okay? And that would be the same for this oxygen here on the left, and this oxygen here on the left side of the right-hand molecule would be 6 minus 1 minus, 246. 6. So it would have a -1 formal charge, again on the most electronegative element, which would be great. And selenium would have a formal charge of, I forgot to draw its lone pair on. Shocker. So selenium's formal charge would be 6 minus 246 divided by 2 is 3, minus 2 for its lone pair. So selenium has a formal charge of +1. So -1 plus 1 plus 0 gives us 0 for our formal charge sum. The most negative formal charge is on an oxygen for both of these, so they are equivalent, okay? So all we can do at that point is say these two Lewis structures are equivalent, so we'll draw an arrow between them to show that those are two equivalent resonance structures. And that's all we can do.